Hello. So I would like to start with a question. The question is whether distributed learning nowadays is robust against arbitrary worker failures. So if I say yes, some of you might think that this is too good to be true, or even worse, this is another bad joke given today's April Fools. But what I will try to do in the next 20 minutes is convince you that this is not a joke, and we actually take a nice step towards answering yes to this quite challenging problem. And we do that with AggregaThor. AggregaThor is a new system that does Byzantine machine learning with a technique called robust gradient aggregation. My name is Georgios Damaskinos, and this is a work we did all together at EPFL with El-Hamdi, Rashid Geraoui, Arsanis Girgis, and Sebastian Ruold. Mehdi, Arsani, and Sebastian are also here with us today. And let's start. So what is the problem that we are considering in a more concrete way? So we're also working on distributed learning. There was two sessions in the morning that talk about scalability and accelerating learning by employing multiple nodes. So this is one of the main motivations for distributed learning. There is another one that is going to be presented right after me. It's focusing more on the federated learning setup, where these devices, the workers that can be seen as, also mentioned as workers, they might have some decentralized data that is better kept private and local on the device. So what we talk about here is what if some of these devices that send updates to a centralized server, namely the parameter server architecture, and the centralized server uses these updates to create a new version of the global model and repeat the procedure in an iterative manner. So what if one of these workers undergoes an arbitrary failure? All right, so by arbitrary failure, I would like to borrow the term from the distributed computing field, namely the Byzantine failure. So a Byzantine failure captures the worst case scenario. Here I have some examples of some Byzantine failures. So for example, a worker can have some software bug in the code that is running, or there can be some corrupted data, or even worse, some malicious user adversarially putting some update, or if you want to see it in gradient descent, which is a popular optimization algorithm, it will try to poison through a poisonous gradient the learning. So how would TensorFlow react into some, let's call it, mild form of Byzantine failure? So what we did here is we have 19 workers, and one of them we simply scale the input, so we have a form of corrupted data. And we notice that even with this simple form of failure, learning doesn't work. So here we have a benchmark classification task for CIFAR 10. You have 10 classes, so you can see that even with a single worker having an issue, the learning is kind of critically damaged. And why is this in a high-level description the case? So you have most of the gradients following some true gradient estimation, and then you have this Byzantine node that is pulling your model towards a completely different direction, and this kind of blows out. So why should we care about this? So there has been many recent kind of adversarial failures, let's call them like that, where you have a majority of let's say workers or people who are giving correct, let's say, tweets, and then there are a few Byzantine ones that give Byzantine tweets. And in the case of Tay, which is a chatbot from Microsoft, the chatbot was not able to distinguish among the two, so it got poisoned by the data of the, let's call them, not correct workers. So let's define our threat model a bit more carefully. So here we have an assumption about the workers being omniscient in the sense that they can have access to any information. The data of all the other workers, the protocol that the server is using, they exchange information, everything. But of course, they cannot be omnipotent in the sense that they can only affect the learning through their response. So they cannot go and change the gradient responses of other workers. And we also have an assumption that the server is non-Byzantine. So the server is trusted. And given this threat model, there has been a recent line of research, which in our paper we kind of classify into two classes. So the first class, we call it weak Byzantine resilient algorithms. And these algorithms, they ensure that learning converges. The second class, we call it strong Byzantine resilience, and it ensures that the learning converges to a state that would be exactly the same as the one that would have been obtained if there were no actual Byzantine failures. Now, for practical cases that you don't have very, very strong adversaries with a lot of computing power, the weak Byzantine resilience can be practical, but the strong one gives you more guarantees with an additional cost, of course. So, given this context, there are some important challenges regarding these algorithms. So what we want really is we want some system support to be able to scale these algorithms into multiple nodes and to be able to compare these algorithms and test new ones. And of course, to have some compatibility with tools that we know how to use and will accelerate things. So given these challenges, I would like to present you our proposal here. So AggregaThor. AggregaThor is a new system that enables scalable Byzantine learning. It's compatible with any application built on top of TensorFlow that uses synchronous stochastic gradient descent. And it employs a component in the networking layer that enables a convergence boost in terms of time that I will talk a bit more in the next part. So let's, this is a high-level overview of AggregaThor in a layered manner. So as you can see here, AggregaThor is a system built around TensorFlow. So we tried to keep the same APIs, the same low-level and mid-level APIs with TensorFlow. We have compatibility with the library and the ecosystem of TensorFlow. And the gray parts are kind of the main modifications the main differences that we have with vanilla TensorFlow. So I will talk a bit more about them. So let's first start with the aggregation layer, where this is kind of where all the magic happens and we are able to kind of tolerate these failures. So what is the aggregation layer? The aggregation layer gathers n responses given n workers and gradients. And that's why we have an assumption about using synchronous stochastic gradient descent. And somehow it computes a single gradient that it pushes to the application layer that then employs it to perform the descent operation, create a new version of the model, and so on. So vanilla TensorFlow, by default, employs averaging inside this aggregation layer. So if we wanted to implement the same algorithm as vanilla TensorFlow. So it just simply creates an average of the gradients. So what we do is we introduce a filtering component before the averaging. So this component, we are able to prove that ensures weak Byzantine resilience. And the design goal of this component is to be able to have accelerated convergence comparing to the alternative Byzantine resilience schemes. We have an assumption on the number of workers, total number of workers, namely n, and f, namely the bound on the workers that can be Byzantine. So f is somehow capturing the level of pessimism that we have about our system. So how does the filtering component works in a nutshell? So for each gradient, it creates a neighborhood. So it gathers the n minus f minus 2 gradients, which are closest L2 distance-wise to the gradient, and then it assigns a score. This score is the distance, the L2 distance with these neighbors. And in the final step, it selects the n minus f minus 2 gradients with the smallest scores. So it somehow wants to keep gradients that look close to their neighborhood. So it somehow wants to capture this majority of responses and filter out some outliers if you want to see it like that. I encourage you to check our paper for the proofs for the convergence and how the assumptions are important for ensuring the weak Byzantine resilience. The second part I would like to talk to you about is the lossyMPI. We call it lossyMPI. It's a new networking option we give as an alternative to gRPC that by default TensorFlow employs. So here, what we have further up in the software stack, we have this aggregation layer that gives us somehow a safety guarantee for our algorithm. So we know that no matter what happens below, we can tolerate up to F faults, up to F arbitrary failures. So we say, why should we fix problems in the network, for example, malformed or delayed packages with TCP that by default TensorFlow employs, and not just push random values up to the application layer, and who knows, maybe it's not so important to solve these values. So this is what we do. We use timeouts, and we replace the missing values with some random ones, and we use UDP for that. And as I will show you in the experimental section, this enables us to have some notable performance boost. So AggregaThor has more things, and I don't have the time, unfortunately, to talk about them, but there is a lot of more detail in the paper. So we have some patches for TensorFlow runtime that prevent the workers from modifying the graph. This is vital for our algorithms to work properly. We have some automated deployment tools, and we also have a scheme for strong Byzantine resilience that we plug to this filtering component that I described before. So let's see some results. So let me come back to the kind of corrupted data attack that I described in the beginning. So as you can see here, by using AggregaThor with gRPC and CPUs for CFAR10 using a CovNet, again, 19 workers, one has corrupted data. AggregaThor is able to mitigate this attack and converge properly. The second part is an important question, which is, so in general, in distributed computing, fault tolerance and Byzantine fault tolerance is a hard problem. So people are using state machine replication and things that are quite costly. In our case, there are some differences in machine learning that enables us to overcome this issue and actually do it with statistics and have a significantly less overhead. So here, I would like to show you the overhead by evaluating our system in an environment with no actual problem. So all the workers are computing fine, the gradients, and the system is deployed with F equals to 4, which means that we tolerate up to 4 faults. So we are over pessimistic about our system. So here we have a TensorFlow, vanilla TensorFlow with the blue line. We have accuracy on the y-axis and the time on the x-axis. So we have our baseline, our ideal baseline as TensorFlow. We have AggregaThor deployed with median, which is an alternative weak Byzantine resilience algorithm, also showing the modularity of our system, the fact that you can plug in your method if it's based on the same principles of aggregating gradients. And we have our filtering component that I described before with AggregaThor, F equals to 4. And we have the only existing system, the only existing framework that does strong Byzantine resilience, namely Draco, again with F equals to 4. So as you can see here, for a bat size of 20, we have an overhead of 47%, and this is significantly better than the alternatives. And an interesting thing is that when we increase the bat size, this overhead reduces. And the reason behind that is the fact that the aggregation and the communication latency per update do not depend on the batch size, but the computation does depend on the batch size. You have less computations for the back propagation. So therefore, the relative overhead when you increase the batch size decreases. And I would like to show you some results regarding the throughput of our system. So again, the same story. We have the same curves here. We have throughput on the y-axis, which shows the number of updates we can do per second, and the number of workers on the x-axis. So one thing I would like to point out here is something that might appear counterintuitive at the first glance is the fact that this red curve here, which is AggregaThor with f equals to 4, is above the green curve, which is with f equals to 1. So in a sense, if we are more pessimistic about our system, we are able to have more updates per second, so we are faster. So the catch here is that we are actually not faster. This is not the end metric that we are measuring. We just can process more updates per second. And why is that? It's because our algorithms, the filtering component becomes more selective, so it pushes to this averaging box, less gradient, so there is less processing, and the whole thing is faster. So as you can see, though, on the accuracy part, this does not necessarily translate into faster convergence. And in fact, with f equals to 1, we converge faster, which shows that the less gradients you push to the averaging box, the more noise you're going to have, so the slower you're going to converge. And for the last experiment I would like to show you is the performance boost that we can get by exploiting an unreliable communication protocol and viewing problems in the network as a form of Byzantine failure. So here we use the same setup, and we have 19 workers, 11 of them are using gRPC, and 8 are using our lossyMPI protocol that I described before. So there are 8 Byzantine workers, and as you can see, for a 10% drop rate that we artificially injected to our network, we can get up to 6 times faster than TCP-based approach. So with this, I would like to thank you for listening and give you some list of the main points of AggregaThor. Namely, we have no constraints on the application, so we are fully compliant with TensorFlow. We have provable guarantees for robust aggregation. We have shown a moderate overhead and significantly better results than the alternative schemes. And we are also able, to get a boost by viewing unreliable communication as a form of Byzantine behavior. I encourage you to check our code that is open sourced, and feel free to ask me any questions. Thanks a lot for listening.
We have time for a couple questions.
Hey, Dave Anderson, Carnegie Mellon. Thank you, that was fun. You motivate this in part by the federated setting, but I'm curious there because you may have a situation where there is a correlation between the data available on each worker. And I totally get how your F+2, F+3 guarantee works in the uniform setting, but if there are correlations, doesn't it seem like an attacker there exist multiple independent clusters instead of one true cluster, and you're going by the centroid of that true cluster. So if they're already fragmented as multiple clusters, doesn't an attacker get more power in that federated setting?
So this is a very legit question. So in general, we haven't addressed the case of having a non-IID distribution in the worker side, and you're right. So if the distribution has certain properties, then there are some assumptions in our algorithm regarding the variance of the gradients, and these assumptions are connected to the norm of the gradients and the variance of the gradient, so there are some constraints there. So if your distribution is really kind of weird, let's say like that, you're going to have problems, as you pointed out.
Thank you.
Sure.
Any other questions? Yeah.
One question, Vladimir Google. Let me know if it's the same question, but maybe I'm just using different words to formulate it. Does your threat model assumes that malicious participants can collude?
Yes, it does assume that. As long as you have up to F malicious participant, they can collude and they can monitor everything and so on.
And maybe one more question for me. So I'm wondering, so this was for the setup where you had the parameter server, right? So I'm wondering whether these methods can extend to, let's say, the all reduce setup. The all reduce. Well, you need
a component that is trusted to execute these algorithms. So I'm not sure whether you can do such a thing in a non-centralized fashion. So, but it's an interesting question.
Great. Let's thank Georgios again.
Thanks a lot.